Welcome to this topic on case studies on eco-resilient interventions. In this lesson, we explore how cities around the world are retrofitting their existing public spaces, infrastructures, and ecological systems to better adapt to intensifying climate risks. Our focus is on three cities, Copenhagen, Chennai, and Portland, each facing very different hydrological challenges, yet each arriving at innovative, eco-resilient strategies that transform the built environment into a tool for climate adaptation. In this session, we will pursue 5 interconnected learning objectives. First, we will analyze global systems by examining nature-based and hybrid systems implemented in Copenhagen, Chennai, and Portland, and comparing how these systems perform in their unique climatic and urban contexts. Second, we will explain adaptation methods, looking closely at how public spaces, streets, parks, marshes, and urban corridors are redesigned to manage extreme heat and flood risks using both ecological and engineered solutions. Third, we will evaluate ecological functions, understanding how interventions enhance water infiltration, evapotranspiration cooling, shading, and hydrological buffering. Fourth, we will compare governance, funding, and community engagement models. Since technical design alone is not enough, implementation depends heavily on institutional coordination and long-term stewardship. Finally, we will identify transferable lessons, synthesizing insights from the 3 case studies to highlight strategies that other cities, regardless of size or geography, can adapt to their own climate challenges. Let's begin by setting the scene with an overview of the 3 cities featured in this module. Each of them faces a distinct climate hazard that has shaped its adaptation strategy. Copenhagen, in Denmark, struggles with acute cloudburst events, short, intense rainstorms that can drop enormous amounts of water in minutes. These storms overwhelm traditional sewer systems and cause widespread urban flooding. In response, Copenhagen has created a citywide cloudburst management plan that retrofits parks, squares, and streets into an integrated blue-green drainage network. Chennai, in India, faces a very different pattern: prolonged monsoon rains combined with the rapid loss of natural wetlands. Decades of urban encroachment have severely diminished the hydrological buffering capacity of the Pallikaranai marsh, dramatically worsening flood impacts. Chennai's response has focused on ecological restoration at a landscape scale, reviving the marsh as a natural sponge. Meanwhile, Portland, in the United States, experiences chronic rainfall throughout the winter as well as increasing urban heat in summer. Instead of large, singular interventions, Portland has pioneered a decentralized, green streets program that installs bioswales, vegetated planters, permeable pavements, and tree corridors across the public right-of-way to treat stormwater at its source. These 3 cities present 3 climate risks: cloudbursts, monsoon floods, and stormwater runoff, and therefore 3 distinct retrofit strategies, each embedded in its local ecological logic. Copenhagen's approach begins with crisis. A catastrophic cloudburst in 2011 caused more than $1 billion worth of damage. It became clear that simply enlarging underground pipes was not sufficient. The city needed to rethink the entire hydrological logic of its urban fabric. The core idea of the cloudburst management plan is to treat the surface of the city not as an impermeable obstacle to rainfall but as an active landscape for water management. Parks and squares are redesigned to operate as dual-use flood basins, lively recreational spaces on normal days, and temporary lakes during extreme rainfall. Streets, too, are reconfigured as cloudburst boulevards, channels that can accommodate large volumes of water flowing safely on the surface. Instead of hiding water in pipes, these boulevards allow the city to slow, retain, and redirect stormwater. This marks a paradigm shift, a transition from a pipe-dominant drainage system to an integrated hydrological network that uses the full 3-dimensional environment: ground, soil, vegetation, and gray infrastructure to collectively manage water during intense cloudbursts. Copenhagen's strategy is advanced through 3 major categories of interventions. First, flood basins and retention parks. Public spaces such as Enghaveparken and Tassingeplads are designed with sculpted basins and flexible surfaces that hold tens of thousands of cubic meters of water during extreme rainfall. These spaces are not merely functional, they remain attractive, social areas year-round. This dual-purpose quality increases public acceptance of flood infrastructure. Second, green and blue streets. Retrofitted roads integrate permeable pavements, bioswales, lowered verges, and surface channels, creating corridors that capture, filter, and convey stormwater. The design ensures that, during a cloudburst, streets become temporary rivers directing water toward larger retention areas or the harbor. Third, hybrid systems linking green infrastructure with traditional gray systems. For example, bioswales manage smaller, more frequent storms, while underground culverts handle extreme events. This layered redundancy is intentionally designed to cope with uncertainty and climate intensification. Together, these interventions redefine the city's relationship with water, transforming parks, squares, and boulevards into components of a dynamic and resilient urban watershed. Copenhagen's technical success is inseparable from its governance model. From the beginning, the city prioritized citizen co-design. Municipal teams held workshops with residents to shape new retention parks and green streets. This not only ensured that designs met neighborhood needs but also helped transform what could have been unpopular flood projects into much-loved community resources. Second, Copenhagen dissolved traditional municipal silos. Departments of transportation, parks, water management, and urban planning were required to collaborate, ensuring that each retrofit delivered multiple benefits, improving mobility, enhancing recreation, and managing water simultaneously. This cross-departmental integration is central to the plan's effectiveness. Third, the Cloudburst Management Plan was institutionalized as a legally binding, long-term strategy, supported by stable municipal taxes and water utility fees. This long-term financial horizon allows the city to implement more than 300 cloudburst projects over several decades. Copenhagen shows that climate adaptation succeeds only when engineering, planning, governance, and community engagement work hand in hand. We now turn to Chennai, where the climate challenge is shaped by the monsoon. The 2015 floods revealed how severely the city's natural hydrological systems had been degraded. Once a vast wetland that buffered the flow of monsoon rains, the Pallikaranai marsh had been fragmented, polluted, and reduced to a fraction of its original size. Chennai's adaptation strategy centers on large-scale ecological restoration, not concrete walls or pumps, but a recovery of the marsh's natural capacity to absorb and store water. In 2022, the marsh was recognized as a Ramsar site, acknowledging its global ecological importance. This approach is fundamentally different from Copenhagen's. Instead of redesigning urban surfaces, Chennai focuses on revitalizing the ecological system itself, restoring its hydrology and biodiversity so that it can once again act as an environmental shock absorber during monsoon events. The rehabilitation of the Pallikaranai marsh involves a coordinated set of ecological actions. The first step is the removal of invasive species that had overtaken native vegetation. These invasive plants alter soil chemistry, block water flow, and suppress biodiversity. Clearing them allows the natural marsh flora to re-establish itself. Second, the restoration project includes reflooding degraded or artificially dried sections. Illegal landfilling and drainage alterations had disrupted the marsh's hydrology. Reintroducing water to these areas helps restore soil moisture and recreate wetland habitat. Third, the team focused on re-establishing natural water channels. Many of the marsh's historic drainage routes had been blocked by development. By dredging and reconnecting these channels, water can once again move through the ecosystem, enabling proper storage and release during monsoon rains. Finally, buffer zones and water quality areas were designated around the marsh. These zones intercept polluted runoff, using wetland vegetation as a natural filtration system. Buffer zones also reduce pressures from illegal dumping and encroachment. In short, Chennai's retrofit is not a single project but an ecological healing process. As restoration progresses, the marsh now delivers multiple ecological and climatic functions. Its primary role is flood buffering. During monsoon rains, the restored marsh absorbs massive volumes of water, acting as a natural detention basin that reduces downstream flooding. The marsh also provides water filtration, cleaning polluted urban runoff as it flows through soil and plant roots. Heavy metals, nutrients, and contaminants are naturally broken down or captured. Beyond hydrology, the marsh is a biodiversity hotspot, supporting migratory birds, fish, reptiles, and a wide variety of plants. Its restored ecological richness strengthens the region's environmental resilience. Finally, the marsh contributes to microclimate cooling. Through evapotranspiration, the large water body and vegetation help mitigate the urban heat island effect, reducing local air temperatures during hot periods. Together, these functions illustrate the power of ecosystem-based adaptation, an approach rooted in ecological processes rather than built infrastructure. Chennai's restoration was made possible only through a broad partnership model. The Tamil Nadu Forest Department provided legal authority, led enforcement actions against encroachment, and coordinated the overall rehabilitation. Local NGOs such as Care Earth Trust served as scientific advisors and advocates. They conducted ecological assessments, guided restoration principles, and bridged communication between government and communities. Research institutions, such as IIT Madras, contributed hydrological modeling, biodiversity surveys, and water quality monitoring. Their involvement ensured that decisions were data-driven and ecologically sound. Finally, citizen groups and volunteers played a major role. They participated in cleanups, monitoring bird counts, and reporting illegal dumping. Their stewardship helped rekindle a cultural sense of connection to the marsh. Chennai demonstrates how multi-stakeholder collaboration can restore an ecosystem that engineering alone cannot replace. Our third case study takes us to Portland, a city known for rainfall that is less intense than monsoons or cloudbursts but highly frequent. This chronic rainfall, combined with aging drainage systems, leads to localized street flooding, degraded streams, and urban heat islands. Portland's solution is a Green Streets program, a decentralized, source control strategy that retrofits the public right-of-way with vegetated facilities. Instead of conveying water long distances through pipes, Portland manages stormwater where it falls. This shift mirrors a broader movement toward water-sensitive urban design, where streets and neighborhoods become part of the city's ecological infrastructure. Portland's retrofits form a toolkit of interventions deployed block by block. Bioswales and vegetated planters capture runoff from adjacent streets. Soil and plant roots slow the water, filter pollutants, and allow infiltration into the ground. Street tree corridors intercept rainfall on leaves and branches, increase shading, and improve microclimate cooling. Permeable pavements in parking lanes or alleys allow water to pass through the surface into gravel layers, reducing runoff and supporting groundwater recharge. Most importantly, these features operate as part of an integrated water-sensitive system. Curb cuts direct water into bioswales, overflow pipes connect facilities, and tree roots improve soil infiltration, all functioning together to treat, store, and convey water in a resilient, decentralized network. To implement green streets at scale, Portland developed a diversified funding and governance structure. A major pillar is its stormwater utility fee, paid by property owners. Those who manage water on site receive a discount, creating financial incentives for participation. Portland also offers community grants, allowing residents, businesses, and organizations to install green infrastructure on private property. This increases local engagement and multiplies the number of installations across the city. Additionally, Portland embraces neighborhood stewardship programs where residents adopt green streets and assist with maintenance, everything from weeding to monitoring. Finally, public-private partnerships require developers to integrate green infrastructure in new projects, contributing to the overall network as part of private investment. Portland shows how financial tools, community involvement, and regulatory mechanisms can collectively scale decentralized adaptation. Having explored the three cities in detail, we turn to a comparative analysis. Copenhagen's risk profile is acute and high intensity, short cloudbursts dropping massive volumes of water in minutes. Its response must therefore focus on rapid conveyance and temporary storage. Chennai faces prolonged seasonal rainfall over a region where historical wetlands have been lost. Its solution is ecosystem-scale restoration to rebuild natural sponges that hold monsoon rains. Portland's challenge is chronic, lower-intensity rainfall combined with summer heat. Its response is decentralized source control, using a citywide network of distributed interventions that address water and temperature together. This slide highlights that climate adaptation is deeply contextual. The form of nature-based solutions must align with the underlying hydrological and ecological conditions. Despite differences in scale, design, and context, these interventions share four major ecological functions. All three systems promote infiltration and storage, removing water from pipes and returning it to the ground. Copenhagen's parks, Chennai's marsh, and Portland's bioswales all help restore a more natural water cycle. They each contribute to habitat restoration, whether through the creation of urban green corridors, wetland regeneration, or vegetated street edges. All three cities leverage evapotranspiration for cooling. Vegetation and water bodies lower ambient temperatures and improve comfort, particularly during heat waves. And they support water purification. Chennai's wetland and Portland's vegetated planters naturally filter pollutants, improving the quality of water entering rivers and groundwater. These shared functions underscore the ecological intelligence embedded in nature-based solutions. Just as ecological functions converge across the three cities, governance lessons also align. Each case is anchored by strong municipal leadership, a clear vision, long-term commitment, and the political will to implement adaptation strategies. All rely on stable, diversified funding, whether through stormwater fees, municipal budgets, or blended public-private investments. Without long-term financing, pilot projects cannot scale. Every city demonstrates the importance of multi-stakeholder partnerships, combining government agencies, NGOs, researchers, and private actors. And finally, citizen participation plays a central role. From Copenhagen's co-design workshops to Chennai's volunteer monitoring and Portland's neighborhood stewardship, community engagement ensures social acceptance, improves maintenance, and strengthens resilience over time. Governance, not just engineering, is the backbone of climate-adaptive cities. Drawing from the three case studies, four lessons emerge as guideposts for other cities. First, nature-based solutions must respond to local climate and hydrology. A floodable park suitable for Copenhagen may not serve Chennai's needs, just as a marsh restoration would not address Portland's chronic runoff on its own. Second, social acceptance and maintenance are essential. Even the most innovative green infrastructure fails without clear maintenance models and community support. Third, hybrid systems increase reliability under climate uncertainty. When nature-based and gray infrastructure work together, cities gain redundancy and robustness during extreme events. Finally, long-term planning enables scalability. Adaptation must be embedded into municipal plans, zoning codes, and budgets, allowing cities to move from isolated projects to comprehensive strategies. These lessons illustrate that eco-resilient interventions are not only technical solutions but long-term socio-ecological transformations. As we conclude, let's summarize the key messages from this module. Eco-resilient public space retrofits are powerful tools for reducing climate risk while adding social and ecological value. Copenhagen, Chennai, and Portland each demonstrate scalable solutions tailored to their own climate realities. Across all cases, the integration of design and governance is crucial. Nature-based systems provide foundational ecological functions, but their success depends on collaborative planning, community engagement, and sustained funding. Ultimately, the most important takeaway is that cities can, and should, transform their public spaces and ecological assets into adaptive infrastructures. With the right governance and ecological thinking, climate risks can be turned into opportunities for creating safer, healthier, and more resilient urban environments.